the way to sustainable energy. Sang-Yuk Lee, Korea Advanced Institute of Science and Technology.
On the 9th of November 1989, I was in the lab performing metabolic engineering of a bacterium.
Thank you. On August 1st, while most of us were enjoying summer vacation, Greenland lost 13 billion tons of ice in a single day. How much is 13 billion tons? It's astonishing. 13 billion tons is equivalent to 28 times the summed weight of entire human population today. So climate change is really a serious problem, as we all agree. One of the main reasons why we are having climate change is due to our heavy dependence on fossil resources, coal, fossil oil, and natural gas. We use them to make gasoline, diesel, jet fuels, and also plastics for bulk use, engineering plastics that are stronger than steel, and also synthetic fibers to make our clothes. How can you avoid this dependence on fossil resources? We can use microorganisms as cell factory to produce chemicals and materials. Why microorganisms? Well, you cannot feed your dog and ask for gasoline. Microorganisms are ethically sound. You eat them all the time through yogurt, fermented foods, without feeling guilty. Also, they can be safely contained in a closed tank called bioreactor, and then they can be disposed after killing, again, without feeling guilty. What do they feed microorganisms? Obviously, we eat bread, rice, meat, or cultured meat, as we heard today. But what about the microorganisms? This can be food for microorganisms. Those biomass we do not eat can be used to feed microorganisms and let them do the job to make chemicals and fuels and materials. Even though microorganisms are tiny, they also run very similar metabolic networks as we do. I'm sure all of you remember this chart from your high school biology class, right? I hope you still do. Well, if you do, you are not normal. Because I look at it every day, but still I don't remember. Those chemicals shown here can be theoretically produced, and they can be classified as natural chemicals. So all of these can be made, but we are not restricted to producing only these native chemicals. We can synthesize new enzymes which serve as a catalyst and new pathways for the production of so-called non-natural chemicals as well. So what I do as a metabolic engineer every day is you identify your product and then you design the optimal metabolic pathway towards the production of that desired chemical. Let me show you how we do that. And if you look at it, here are cells. If they can move. Maybe I go back and then come back down. Okay. So cells are happily growing. Now you are interrogating the cell metabolism at the DNA level, RNA level, and protein level with controlled design of the fluxes. And then you can make these cells not only just grow, but produce the chemicals of interest. Once you design these microbial cell factories, now you can bring it to the bioreactor. You're looking at bioreactor. In this particular case, it is yeast. It's growing inside. And obviously, you have a control panel where you can control not only the pH, but also the dissolved oxygen, also nutrient feeding strategy, I'm very good at cultivating cells to very high density, that is number of cells per same volume. How much we grow cells? Well, we can grow E. coli to 120 gram dry cell weight per liter. Well, probably you don't have any idea what that means. It is similar to filling this room with 2,000 people and make them live happily for 200 years while producing the desired chemicals from non-edible biomass. Now, what have we produced using metabolically engineered microorganisms? We have produced propanol, butanol, 1,3-propanediol, 1,4-butanediol, 2,3-butanediol, 1,4-diaminobutane, 1,5-diamинopentane. If I continue, probably you will hate me. But we produce a lot of different chemicals. But let me showcase a couple of them. So first one is gasoline. Gasoline is, by definition, non-natural chemical. Of course, it's driven from fossil resources. What we did was we engineered fatty acid biosynthetic and degradation pathways, which is necessary to make fatty acids to be used for cell membrane biosynthesis. Unfortunately, the carbon lengths of such fatty acids are quite long, not suitable for gasoline production. So we did engineering to shorten the carbon lengths of fatty acids first, and then we introduced three-step pathway. One of them was recruited from different bacterium, and another one recruited from even plant, and then reconstructed the entire new metabolic network. Now cells are making gasoline by fermentation on glucose derived from non-edible biomass, now spitting out gasoline by fermentation. Furthermore, we wanted to tackle the issue of biodiesel. Biodiesel nowadays is produced from plant oil or animal fats. And plant oil, represented by palm oil, for example, is food. Especially in Southeast Asia, it's precious food they have to eat every day. So here's food versus fuel issue, and we don't want that. Can we produce biodiesel from this? So we found a bacterium called Rhodococcus. We can grow this cell in a fermenter using glucose as a carbon source. They will fill the entire cell with a lipid, and that's why it's called oleogenous bacterium. And then we did perform metabolic engineering so that these oils are degraded into fatty acids, and then we let them produce ethanol at the same time, and also we combine them through wax ester synthase to make diesel. So now after the fermentation on glucose, this engineered bacterium produce biodiesel with quite high efficiency. Let me switch a gear to plastics issue. As we all agree, and as we heard, plastic accumulation, especially the waste plastics, is a significant threat. Let's look at the statistics first. This year alone, human beings will produce 350 million tons of plastics. Over the last 70, 80 years, we produced more than 8.3 billion tons of plastics. Where did they all go? Do you know? Among them, 9% recycled, 12% incinerated. Well, by incineration, at least you get some energy. And 79% landfilled. And what happened to those landfilled plastics? Well, they will be weathered. Some of them go to the river, and then ultimately to the ocean. They form a great Pacific garbage patch, and planktons eat those weathered microplastics. Fishes eat those planktons, and we eat those fishes. So, how much plastic we eat? We eat 1 credit card per week, which means we eat 1 toothbrush per month. Of course, most of them will get out, don't worry. However, some nano-sized ones will not. These guys. So can we do something about it? Yes, we can do something about it. We can replace them with biodegradable plastics. Nature provided a pathway for the production of biodegradable polymer. In this particular case, polyhydroxyalkanoic acid, which I'm not going to go detail, but you can use metabolic pathways to synthesize true polyesters. Metabolic engineer like myself, how much we produce? A lot. Look at this picture. This is single E. coli cell transmission electron micrograph, and those white granules inside the cell are all plastics. So we basically fill the cell with plastics. Cell's dead. I don't care. I need plastics. And again, ethically sound for microorganisms. By using such biodegradable plastics, we can complete the eco-friendly cycle of carbon. So from sunlight, CO2, water, you get biomass, and those non-edible biomass can be used to synthesize by fermentation the plastics we need, and then we make articles we want to use, and then if you want, you can recycle them. It's summer plastic. If it's degraded, it completely biodegrades and meets the perfect carbon cycle. Microorganisms are versatile, but not omnipotent. So we cannot make a lot of different polymers we need every day. We need rubber for tires, we need the engineering plastics, but in that case, you can make monomers that can be used for polymer synthesis. So can you produce those monomers? Yes, those are the chemicals I mentioned earlier. And let me show you one example. Now you're looking at Korean cows, or Korean cows are looking at you. We isolated bacterium called Mannheimia succinisi producens. We named it succinisi producens because it produces so much succinic acid. And by fermentation, we can produce this important 4-carbon dicarboxylic acid that can be used for not only polyesters, but also for nylons or engineering plastics. We can also produce 1,4-butanediol, which is important chemical to make spandex, and we need spandex. Otherwise, when I jog, my pants will be all torn apart, and it's not very pretty sight. So we need spandex. Now we can make a sustainable spandex as well. We can make PET, which you use every day. We produce 19 million tons of PET every year, and it's increasing. This is PET. The cap is not. This is polypropylene. This is PET, polyethylene terephthalate. PET comprises 2 monomers, monoethylene glycol and terephthalic acid. We make both monomers by fermentation. So 100% bio-based PET can be made, and you can recycle them. All the products I talked about are organic chemicals. Well, that's obvious because we use organisms, microorganisms or organisms, to produce these chemicals. However, we found that we can actually make inorganic materials as well. When we are exposed to heavy metal ions, obviously you know that it's very toxic. And same applies to microorganisms. So through the evolution, they have established this heavy metal detoxification mechanism using proteins to reduce these heavy metal ions and then form nanoparticles. Based on that finding, we scanned through entire periodic table what kind of nanoparticles we can make, and we made various nanoparticles, some of which are useful for quantum dots, some of them for nanomagnets for medical therapy, and also energy storage material, room temperature gas sensor applications, etc. So, truly, microorganisms are versatile. Having worked on this topic for many years, we recently compiled all the chemicals we can make through biotechnology. Now, the center pathway is the pathway we know through biology class. Starting with glucose, xylose, glycerol, whatever carbon source you start with. Now here's the glycolytic pathway, and then TCA cycle, which you probably remember. And then from those intermediate metabolite, you can add the reaction pathway to make all these chemicals. And this is not just all of them. The entire pathway looks like this. So we are able to produce so many different chemicals through biotechnology, some of which are very efficient, some of which requires much more improvement, but at least we have platform technology for the production of chemicals and materials. So which wall am I trying to break down? The wall is our heavy dependence on fossil resources. We are living in a crucial time when our decisions and actions will determine the future of our children. By breaking down the wall of dependence on fossil oil, we can change the world by not changing it at all. Thank you.